Okay, hi everybody. Welcome to the third lecture of data mining and machine learning, and this will be the first part of our classification module. And before we get started, let me show you something. This is an apple, and this is a banana, and this is another apple, and another apple, and another banana. And now my test question for you. So this is a new fruit you haven't seen yet. Which kind of fruit is this? So we are going to play essentially the same game with our machine learning algorithms this week. So we will talk about the classification problem. So the classification problem talks about objects which belong to a finite set of different classes. So this different set of classes might be only two, like apple and banana, but we could also have like more classes like plums and lemons and pineapples, of course. We will communicate this classification problem to our computers and machine learning algorithms by taking features of these objects. So we could measure the length of the objects, we could measure the color, maybe sugar content, diameter, and other chemical analysis. Or we could just take pictures of these fruits and take these pixels of these pictures as input to our classifiers. But the general principle is that we will take some set of features describing this object, and then we will have labels. So we will have a hopefully large collection of example objects, and this will be called our training set. And somebody has done the work to label these examples. So for example, we could encode now banana as 0 and apple as 1. So we will compile a training set which contains the feature vectors of our objects plus the ground truth label. And we will provide that to our machine learning algorithm, which whose goal it is to create a model which hopefully extracts the useful information or the principle which distinguishes apples and bananas. And the general power of the classification problem is its generality. So we could do something silly like classifying fruit, or you could also figure that these fruit are actually patients in a hospital, and rather than taking features like length and color and sugar content, we take medical measurements of these patients. And we want to classify whether these patients are seriously ill or healthy. So essentially we want to diagnose these patients. Or another example, look at your inbox folder, so of your emails, and you get, there are emails which are from your friends and colleagues, and there are emails which are spam. And essentially you want to distinguish based on some features you take from this image whether they are good emails, so normal emails, or spam, which try to sell you Viagra. So it doesn't really matter in principle about which classification problem we talk. So we don't need to solve the same problem for fruit classification or for classifying patients, for diagnosing patients, or for classifying spam. So the learning algorithms we will derive will, in principle, work for any domain where we work with input features and class labels. So let's now look where we are in our course. So last week we had a general intro and discussed optimization and linear algebra. Now this whole week will be dedicated to classification. So this will be the content of today's lecture, and random forests and support vector machines will be discussed in the next lecture. So in particular today we'll discuss about the general background of classification, of the classification problem. So we'll discuss our basic assumption how our data was generated by some true underlying distribution, and we'll discuss the true error and base optimal classifiers and these things. And then we'll discuss three simple classifiers. So in particular, k-nearest neighbors is one of the simplest classifiers at all, but highly effective often and surprisingly effective. And also naive Bayes is a very simple and cheap classifier and also works surprisingly well. And decision trees also work pretty well and are in particular nicely interpretable by humans. Like this, in principle, decision trees are a machine learning algorithm which can be nicely understood by humans. And then finally for today, we will talk about evaluation of machine learning algorithms and how a proper pipeline, how to train them. Okay, let's get started with our general discussion of the classification problem. So in this section, we will discuss the classification problem from a fairly general angle. And in particular, we will discuss the so-called IID assumption, which says that our data items have been sampled independently of each other and are identically distributed according to some underlying distribution P star. We assume this distribution exists and has produced our data in IID fashion, but in general, we don't know this distribution. Then we will define what a learning algorithm is and what a classifier actually is, and we will define our principal learning goal, minimizing this true classification error. So this is a principal and ideal learning goal, but rarely realizable in practice. And however, so this classifier which achieves this goal we call Bayes optimal classifier, and we will talk a bit more about this. So here we see the principal setup of our classification problem. So the classification problem aims to label data items with a finite set of classes. So for example, we might want to label fruit with the label, so apple versus pear, or we might have images of handwritten digits and we want to recognize which digit is actually represented in these images. This is a fairly easy task for humans, but surprisingly hard for computers. Or we might have patients and we want to classify them into healthy or ill. And the common theme here is that we assume that the data items can be described with some feature vector x. So this might be color values and shape values and maybe sugar content of fruit here. Here this might be just the pixels, all the pixels of our images. And here this might be medical measurements of our patients. So we describe our objects with a feature vector x and we encode the class in a variable y. So y takes one out of these finitely many values. So y is a discrete variable. So this is our target and this encodes our class. And we have the input features and we want to predict the class. So what is now actually training data? So we assume that we have n training examples for training. So we feed that to our classifier and we want to our algorithm and we want to learn a classifier. And the training example is just a pair of input feature and class value. And we have n of these pairs. So this is our training data, just a collection of n pairs input feature together with this class value. So in the training data, we actually know the underlying, the class, the ground truth class. So somebody has annotated this for us. And the basic assumption in classification, but really in machine learning, is often that the data has been produced in IID, so independently and identically distributed. So we assume that each of these training examples here is produced by drawing from a distribution P star. So P star is a distribution over feature vectors and corresponding labels. And each of these examples is just drawn from this P star. The samples are independent of each other and they are identically distributed to this P star. And so this P star, essentially we assume it exists, but we don't know it. And so this distribution is in general complicated because reality is complicated and reality is uncertain. So we don't know this distribution and it might be very complicated. Think about image classification. So we have this distribution essentially encapsulates all the uncertainty we get from different cameras and from different lighting conditions and from different angles, and also that people make mistakes. So like there's a lot of uncertainty how our data actually was produced, and we just encapsulate this away in, well, some unknown distribution P star. But we assume that the data is independent and all the samples are identically distributed to this P star. So this is a very common assumption, IID. Now, what is actually a classifier? So a classifier is just a function h, which takes an input vector x and it produces a label y hat. And we distinguish the predicted labels by equipping them with this hat here. So the ground truth labels don't have this hat and the predicted labels have this hat in our notation. So for example, we have a sample xi, so this is describing our ith object, and we feed that into our classification, into our classifier, this function h, and produces this predicted label yi hat. So a classifier, simply a function from input features to class label. And we can now describe what a learning algorithm is. So a learning algorithm is actually also a function, but a second order function or a higher order function. So a learning algorithm is a function which takes a whole data set, so which consumes our training data set and it produces a classifier h. So it takes this whole training set as input and it produces this function h, this classifier h. So what is actually our goal for classification? And the ideal goal we want to achieve is to minimize the true classification error. So figure that we have trained a classifier h, or we just want to test a particular classifier h, so we can also take an arbitrary classifier h, so we have this h given. And then the true classification error of h is simply this is the probability of making an error. So recall the training data is actually drawn from some distribution P star. And now we take one more sample from this P star, which is not in our training data, but essentially we take a test sample and we are uncertain about the input features and the labels. So if input features and labels are random variables, and we ask how likely will we misclassify the next sample. So this is the true classification error. We can also figure it as this expectation here. So here we have, in this expectation, we have this indicator function, which is just 1 if we make a misclassification. So, and this expectation goes over this indicator. So this indicator measures whether we make a mistake for feature vector x and y. And again, so this is an expectation. So these are x and y are random variables drawn from P star. And we measure, are we doing a classification error or not? And then we compute this expectation over classification errors. So this is the same thing, and therefore we have these two different interpretations. Probability of error for a random sample from P star, or also the average number of misclassifications on a very large test set. So this is a very worthy goal, and well, our ideal goal we want to achieve when we learn classifiers. However, there's a problem that this true classification error cannot be computed exactly in practice. And so why is this? So what is the inherent problem when we want to compute the true classification error? So think for this about this for a minute. So this is out of reach, but however, we can still define a classifier which actually minimizes the true classification error. So we cannot compute the true classification error, but there still exists some classifier which minimizes this. So some classifier will minimize the true classification error. And this, we call this classifier H star, and we give it also a name. So we call this classifier base optimal. So this is the best classifier we can come up for our classification problem, and we call this the base optimal classifier. So a principal way to come up with the base optimal classifier is to use our true underlying distribution P star, so the distribution which generates our data. And if we have this distribution, we can also compute the conditional distribution of label given input features. So if we get now an input feature, vector of input features here, we get a distribution over the class labels and the natural classification strategies to pick the class with highest probability. And it can indeed be shown that this yields the base optimal classifier. And moreover, if we multiply here on the right with the marginal distribution over our input features, So this does not depend on the class. So therefore these lines are equivalent. We see that we can also use directly the joint distribution, the original joint distribution over label and input features. So this is a principal way to construct the base optimal classifier, but similarly as for the true error, so this is not a practical algorithm. And again, please think for a short moment about why we cannot use this in practice. So this concludes this first section. So we discussed that our samples, our training samples, are produced from this unknown distribution P star, a joint distribution over features and class label, and a common assumption is this IID assumption, that the samples are produced independently and are identically distributed. And we defined what a classifier is. So a classifier is just a function from input features to a predicted label. And the learning algorithm is also a kind of function that it maps a whole data set to a classifier. So a data set as input and a function, this classifier as output. And we defined our ideal goal to minimize the true classification error, which is, however, out of reach in practice, typically. And we defined the classifier H star, which actually achieves this ideal goal. We defined to be the base optimal classifier, and we also discussed that the true distribution P star actually gives raise to the base optimal classifier. So if we knew P star, then we also would have the base optimal classifier.